A power series has the form the sum as n goes from 0 to infinity of a sub n x to the n, which expanded looks like a sub 0 plus a sub 1x plus a 2x squared plus a 3x cubed plus dot dot dot, and so on. They go on infinitely far. Another way to refer to a power series is essentially it's an infinite polynomial. When we consider convergence of a power series, we mean values that, when put in place of x, will result in a finite value for the infinite sum. To see what I mean, consider the convergence behavior as this of the sum as n goes from 0 to infinity of x to the n, which, as you know, is 1 plus x squared plus x cubed plus dot dot dot. This thing converges if the absolute value of x is less than 1, because what we essentially have is a geometric series, except instead of writing it as the sum of r to the n, we're writing it as the sum of x to the n. As long as the base in magnitude is less than 1, this will converge. From this, we can write down the radius of convergence. I'll say that it's 1 now, and then I'll show you what it is in just a second. The absolute value inequality of absolute value of x is less than 1 also gives us an interval. It's known as an interval of convergence, and in this case, it's the open interval from -1 to 1, right? We aren't including the endpoints because if the base is 1, this thing will not converge. Let's look graphically at what the interval of convergence is. It's not a very exciting graph, I'll grant you. It's just the open interval from -1 to 1. And I'm going to highlight that. Now this is the center of this open interval is 0, of course, and the distance from the center, that 0, to the endpoint, 1, is what the radius is. Right, and it should make sense. It's kind of, you're thinking about a circle, right? The radius is like halfway across the interval. In this section, for any particular given power series, our primary concern mostly is going to be finding the radius of convergence and finding the interval of convergence. For example, let's consider the sum as n goes from 0 to infinity of x plus 2 to the n. This is what's known as basically a shifted power series. Instead of the base being x and having the expression x to the n, we have a base of x plus 2. So we have x plus 2 to the n. This is basically shifted to the left by 2 units, just like you would shift a graph. This will converge if the absolute value of the base, x plus 2, is less than 1. That leads us to an absolute value inequality. -1 is less than or equal to x plus 2, which is less than or equal to 1. Subtracting 2 from all 3 parts of this inequality will give us that x is between -3 and -1. Thus, we have a radius of convergence, which is 1, and an interval of convergence, which is the open interval from -3 to -1. Visually, this looks like the open interval on the x-axis from -3 to -1. We can see that the center of this interval is -2. That's that shift I was talking about. And I'll highlight there the interval from -3 to -1. And then the distance from the center to one endpoint of the interval is the radius. We aren't going to be spending time in this section graphing this on a number line. I'm just giving you something for it to hang on to. We have a theorem about convergence that seems intuitively clear, but we aren't going to prove. The theorem says, for a given power series, say the sum as n goes from 0 to infinity of a sub n x minus a to the n, there are only 3 possibilities. One is that the series converges only for one value x is equal to a. That would mean the base is 0, so you clearly have convergence. In this case, we would say that the radius of convergence is 0, and the interval of convergence really is just the set that contains a. The second possibility is that the series converges for all real numbers, so for all x in the real number system. In this case, we would say that the radius is infinity, and the interval is the entire real number line, -infinity to infinity. Those are kind of special cases. The third case is the one that's more common. There exists a number r greater than 0 such that the series converges if the absolute value of x minus a is less than r, and diverges if the absolute value of x minus a is greater than r. And this was the case in the second example, actually the first example too, that we looked at. If x is between -3 and -1, it would have converged. Everything outside of that interval would give us divergence. Oh, and then back to here. We did not include the endpoints in the interval of convergence because the base of a geometric series has to be strictly less than 1 for the series to converge. However, generally speaking, we do have to find out what's going on at endpoints. And generally speaking, convergence at endpoints is explored case by case. I don't just mean each problem is different. I mean, in each problem, you have to test the left endpoint and the right endpoint separately. You'll see examples of that. To determine which of these we have, that the series converges only for a single value of x, or the series converges for all real numbers, or that we have an interval, and really I should say a bounded interval, we are generally going to use the ratio test. So what I wrote, we will generally use the ratio test to determine which of the above is true.